on Tuesday, the 23rd, everybody shifted to intervention. That is not an experimental that has 3 demonstrations of the effect at one point in time. Does not meet the criterion. All right, but so somebody came up with this great idea, and they said, well, you know what we can do? We can have one kid in January, another kid in March, and another kid in April. See, here's actual time down here. And it's much easier to actually run that study. But once again, there were 7 data points in baseline, 7 data points in baseline, 7 data points in baseline. That is not a single case experimental study. The key is that you actually get different lengths of baseline. You want to control, I want you to think about this. Remember, one of the threats to internal validity is instrumentation. It's the process where you say, you know what, after doing it 3 times, they figure out how it works. And their data sort of change by the 4th or 5th time. And you get used to, all of you have worked with situations where the initial time you did it was different than as you did it repeatedly. So part of what we want to do is we want to control for that, and we want to control for the absolute time of the year, all those different variables that are continually changing, the amount of virus that's in the air. So this is the pattern. The pattern of a concurrent multiple baseline is same time, different lengths of baseline. All right, so now a non-concurrent actually looks like this. You run at different points in real time, and you present here. The key is that you still have different lengths of baseline. So a non-concurrent multiple baseline still controls for length of baseline. It does not control for the absolute time of the absolute time. That's what it doesn't control for. So it has certain features that work, some that don't. So now we're all on the same page? Okay. So the second thing, I loved when David was going through this set of percent of non-overlapping data. All right? This comes out of Texas. This is a Texas graph. Should be in green, or have horns on it or something, I don't know. Here's the point. The thing that I want you to recognize, in those 8 figures, the data are all the same. The data are all the same. Second, this is an example, is this an example of assessing a basic effect or an entire study? Which is it? Basic effect, yes, you're okay. I don't care what Mia says. You're all right. All right, so here we go. Now, if that's the case, I want you to look at how much people are trying to struggle to say, is there a basic effect? All right. And here are the numbers, right? So, I mean, come on, these are whopping numbers. This is 0.86. Right? Even my brother-in-law knows that. He's an attorney. He knows 0.86. That's good. Okay, so, but the problem is we're asking the wrong question. And I want you to always come back to it. Don't do statistics because you know how to do a statistic. Do statistics because it answers the question you want. So a basic effect, even a fuzzy basic effect, all right? Ask the question, does the pattern in phase 2 differ more than we would expect from observed and predicted patterns defined in phase 1? Now here's what I want to introduce. Talking about the observed pattern in phase 1. Look at the observed pattern in phase 1. Now come on. You're scientists. You have been taught when somebody says, look at a set of data and tell me what it says, You say, look for a measure of central tendency. I'm going to talk about the mean or the median. Look for, not just central tendency, but variability. So what's the range about the mean? What's the slope? You can describe, come on, these data are very different from those data. Right? Okay, that's cute. But you know what that's doing? That's adopting a really static sort of model. So partly it's like saying, I'm going to say that set of data is best represented by that data point as the average, right? That data point is the average. And we're going to pretend, my goodness, there's level change. Well, yes, there's level change, cowboy, but that's not what we're about. Okay, I want you to look at the second part. I want you to compare the data in phase 2 with observed and predicted. Now, David used the really critical concept when he was presenting before, and he talked about the fact that the data are serially dependent, right? They're autocorrelated. So these are data that all came from Elliott. There's Elliott, 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 Elliott. Okay? They are not independent data points. You may not have a mean. That is not, you're not able to treat those as independent events. Those are all from Elliott. And they're not randomly organized. They're organized with respect to time. Okay, I'm a little melodramatic. Come on, it's after lunch. Give me a break. Okay. Now, I want you to come back. Come on, I want you to be thinking. Do these data differ from observed and predicted pattern? Well, so tell me what the pattern is. And to do pattern, level, trend, variability. All right? So calculate the best fit straight line. We know what the average is. We're going to calculate the variability about the best fit straight line. We're going to calculate some measure of range. You can use a standard deviation. You can use the range itself. But you got some confidence intervals. All right? So I'm describing that, but now what I want you to do, come on, now you got your growth curve stuff. Come on, we don't have to make this linear. We can make this curve linear. But tell me what you would predict. Tell me what you would predict. And you can do this as a statistician. You can say, what is the conditional probability or what is the likelihood of data about that extended line? You can also talk like a normal human. You could say, tell me the extent to which you would bet the next month's salary, for those of you who have salaries, right? Would you bet your next month's salary that you could identify a range within the next 3 data points would be? So would you put them down here with this median line? You say, this is the median. Wouldn't you put them down here? No, you wouldn't do that. You're going to put them up there. Okay, now, when you talk statistics, you need to be able to translate into normal human. So be able to think, to what extent do we really think that the data in the phase 1 reflect and project and predict the data in phase 2? And I would argue that the data in phase 2 are dramatically predicted by the pattern we see in phase 1 because we treat the data as autocorrelated. We know that they are not randomly occurring. They're from the same person in sequenced time. Those are not randomly ordered. Because of that, I'm looking here and I'm saying, there is no basic effect. This is just basically what we would have anticipated. Now we've got to know more about the dependent variable because, I mean, a lot of things you can't just keep going up forever. You're going to get asymptotic patterns and things of that nature. But that comes from the logic model. Okay, so One, I want you to be able to, now that you know about designs, you've got a logic model, you've got a research question, you're going to be able to build a design. Whether you're doing a reversal or multiple baseline or alternating treatment, that's for another. Now I want you to start saying, well, okay, if that's the case, how do I actually do this interpretation? And I'm telling you, if by chance you want to publish, get a grant done, or contribute to the world's knowledge, you need to do single case research that includes first visual analysis and then also includes a measure of statistical effect. So is it statistically unlikely to occur, and is there an effect size that would help us to build an understanding of truly evidence-based practice? Okay, so now you're excited. You're ready to rock and roll. So let's do the first part. How do we actually document experimental control? You do it by having a design where the design allows testing and the data document 3 demonstrations of a basic effect, each at a different point in time. Now, I'm going to give you access to a website, www.singlecase.org. And we're going to go there just in a little bit, but I'm actually going to walk you through pieces of it right now. But tonight, I actually want you to go to www, and I'll show you how to get on, and we'll go through that. But so here we go. Now, and so Peter, this is, I want you to start building your computer or your statistical algorithm. So if you're actually going to do a statistical model of a group of a ABAB design or multiple baseline design, you need to be able to control for all of the typical variables. So the easy ones, the ones we all know and love, the ones you feel good about, level, trend, and variability. All right, when you examine each phase, baseline, phase 1, phase 2, phase 3, whatever you've got, right? With each one, tell me what the average is, tell me what the trend is, and tell me variability. Level, trend, and variability. Come on, those are ones that you already know. We're good. You got multiple levels. You can model those. No trouble. All right, but now, if I'm going to look at a basic effect, I look at change in level, change in trend, change in variability. I'm going to look at the extent to which there's overlap. Overlap is a credible variable. It's just overrated. All right? I also want to look at immediacy of the effect. Now, immediacy of the effect is related to the amount of time between the intervention and when you would say the data no longer follow the prior pattern. Immediacy of effect is going to be influenced by your logic model. So in some cases, you would predict. You do not predict giant weight change from one day to the next. You would expect gradual. So the logic model determines what you're going to count as an immediacy effect. In oral reading fluency, for example, the immediacy effect is not in level, but in shift in trend. If the slope changes, so you need at least 3 data points, rapidly, that would count as an immediate effect. Now, the one that is oftentimes missed is consistency in similar phases. Do the baselines look the same? Does phase 1 after intervention look the same? Does, in a reversal design, do the 2 treatment conditions look the same and the 2 baselines look similar? Do they look more similar to each other? If they do, that increases your confidence. Now, there are a set of other things that are becoming, that have been thrown out and are becoming things that we're looking at. So there's one measure of immediacy of effect is called the intercept gap. So I'm going to introduce that. It's not something that is being used a lot, but you should know about it. A second is within the multiple baseline design. One of the things that is most often missed, all right, from now on, this day forth, when you look at multiple baseline designs, I want you always to to include a vertical analysis as well as a horizontal analysis. So this is going to be a big thing that I don't want you to miss. The other is in alternating treatment designs, too often what people get caught up with is expecting everything to be the same. So you're looking at change over time. Alternating treatment designs are much more complicated than people typically give credit for. All right, so Peter, minimal design, minimal algorithm, level, trend, and variability. You thought, okay, I got that, that's good. But now I want you to build in overlap, immediacy, effect, and consistency of similar phases. All right, so that starts getting a little more complicated. Now I want you to think about the amount of variation in each one of those variables, and 6 things, each with 3 or 4 levels. It starts getting a little more complicated, right? Then you want to go to Greek figures. Okay, so let's do this. The way you teach a compound discrimination, when you teach